In section 7.6, we're looking at sine and cosine ratio. In 7.5, we looked at tangent ratio, which was our first of our three trig ratios. This section, we finish it up. So, if we look at where we're starting here, we have triangle ABC, and that's a right triangle, and we're going to focus on acute angle A, which is this angle here. As with tangent, if you think back when we looked at it, tangent we said was opposite over adjacent. We're going to get two new ratios today. We're going to have sine and cosine. So the sine of angle A, and this again is just a ratio, so we're going to say the sine of A equals the leg opposite angle A over the hypotenuse. So in this case, we could say that sine of A is equal to the opposite leg, BC, over the hypotenuse, AB. We'll also just shorten it up eventually and say that sine equals opposite over hypotenuse. Our second one is cosine, and cosine, so we'll say cosine of A, will be the leg adjacent to angle A over the hypotenuse, which in this case we could say that cosine of A equals, let's see, the adjacent would be AC, AB would be the hypotenuse, so AC over AB, or just sum it up as cosine equals adjacent over hypotenuse. Now we paired these two up with the one we talked about previously, which was tangent being opposite over adjacent, and we get a way to remember these three of them, and that is so, ka, toa. And it's a way just to remember the order that these go. And it's kind of a good approach just to have it memorized so that when you need to refer to one of them, maybe not all of them, but just one of them, you have something to reference. So we say so, or sine, is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So later on, next section, when we actually look at solving right triangles, and it won't be so much focused on sine and cosine, this will be really useful to help us identify which one we need. So let's just look at sine and cosine for this section. So first we're just going to start off basic ratios. We said that sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. So if I look at sine of S, the opposite of S is 63. And the hypotenuse to S is 65. So we could say that sine of S is the ratio of 63 to 65. We'll just leave it as a fraction for now. If it asks for it as a decimal, we could just divide and have a decimal. Sine of R. Opposite of R is 16. Hypotenuse is 65. Cosine of S, that's adjacent over hypotenuse. So adjacent to S is 16. Hypotenuse is 65. And cosine of R, adjacent to R, is 63. Hypotenuse is 65. So we have that ratio. Now if we look briefly at the relationship between these, actually, we notice that sine of one angle is equal to the cosine of the other angle. They're the same thing. And that works because if we look at sine of S, that's opposite over hypotenuse. Cosine's adjacent over hypotenuse. Well, the opposite of one angle is the adjacent to the other. So they should match up. Maybe later on this gives us options to which ones we want to solve, if we knew an angle in particular, but it's just something that occurs as we start. So, here's four of them to look at. Maybe you want to pause it, try these on your own, and then see how you did. But as we go through, we first get sine of x is what we're looking for. And we said earlier sine is opposite over hypotenuse. So if I'm looking at x, the opposite leg is 8. The hypotenuse is 17, so it would be 8 over 17. They want that as a fraction and a decimal. So 8 over 17, put that in our calculator, we get about 0.4706 as our decimal. And then let's do sine of y. Opposite to y, opposite leg, is 15. Hypotenuse is 17. We divide 15 by 17 and we get about 0.8824 to 4 decimal places. Now, next one we have 15, 20, 25. We're looking for sine of x. Sine of x is opposite leg, 15, over hypotenuse, which is 25. That reduces to be 3/5, which is just 0.6. Next, we're looking at sine of y. So opposite to y is 20. Hypotenuse is 25, so 20 over 25. That reduces to be 4/5, so it would be 0.8. Moving down, now we look at cosine on these next two. Cosine is adjacent over hypotenuse. So cosine of r, this should be r right here. Cosine of r is going to be adjacent over hypotenuse. Well, the adjacent is 9, but we don't know the hypotenuse. Well, this is something we've actually done already in this chapter. It comes down to Pythagorean theorem. We know these two. We need to find the hypotenuse. So if we said 9 squared plus 12 squared equals our hypotenuse, let's call it h squared. I get 81 plus 144 equals h squared. That's 225 equals h squared. If I take the square root of both, I get h is 15. So now we go back to the problem. Adjacent was 9 to r, 15 is the hypotenuse, so I could say 9 over 15. I can reduce that fraction, divide by 3, so it's 3/5, which is 0.6. Next we go cosine of s. Adjacent to s is 12, hypotenuse is 15. This reduces, like our other one, to 4/5, which is, like we said earlier up here, 0.8. Last one here, I have 16, 30. It looks like I need the hypotenuse again. So I'm going to do 16 squared plus 30 squared equals h squared, where h is my hypotenuse, SR. 16 squared is 256. 30 squared is 900. That leaves us with 1,156 equals h squared. I sure hope that's a perfect square. If we take the square root of that, we get 34. We lucked out. So 34 is now our hypotenuse. Now I can find cosine of r. Adjacent leg is 30. Hypotenuse is 34. That reduces to be 15 over 17, which is 0.8824. And then we get cosine of s, adjacent over hypotenuse, is 16 over 34, or 8 over 17, which comes out to be 0.4706. So what we did here was we took the triangle and we just wrote the ratio that exists, either sine or cosine, based on the side lengths we knew. What we're going to do later is we're going to use angles. We'll take that actual angle, plug an angle in here, and solve for missing sides. Now, before we do that, though, we're going to look at a couple terms, and these terms are going to come to apply as we start to look at more application problems in this section. And first off, if we look up at an object, you're standing looking up at an object, the angle your line of sight makes with the horizon line is called the angle of elevation. So you're standing, this person's standing down here looking up at their friend. There's a horizontal line that goes to the horizon, and there's this line that they're staring on. That's going to be our angle of elevation, so it's looking up. Conversely, if you look down at an object, the angle your line of sight makes with the horizon line is called the angle of depression. So this person up here is now looking out horizontally, but they're looking down, and that's an angle that goes down. Now we're going to use these in problems, and it comes back to setting up and using our trig ratios. And just imagine here that this person's looking out, and I can actually make a right triangle here. And maybe this is a scenario where we know the angle of elevation. Maybe we know the distance that they are apart, but we want to know how high up the person is. In that case, we know this value. We could solve for this one and having an angle. Maybe we know how high up they are, but we want to know how far they are. So it just sets up for different problems we could find. The other thing to look at, since I'm looking out at the horizon line, these two angles are actually the same. They're alternate interior angles because we have parallel lines cut by a transversal. So if I ever had to adjust the problem a little bit to make it fit into a triangle a little nicer, I do have that option available to me. So let's look at some examples here. First off, we have a guy skiing down a hill. So we've kind of transposed some triangles over here. But you're skiing down a mountain, and the altitude is 1,200 meters. Well, we have meters here, we have feet here. Let's just call it feet. Make it consistent. Looks like we got a typo there. So the distance from here all the way to the bottom is 1,200 feet. The angle of depression, the way as they look down the hill, is 21 degrees. We need to figure out how far they're going to travel, which is that hypotenuse. So looking at this problem, we see a triangle, we have an angle, we have a hypotenuse, and this is either the adjacent or the opposite leg to the angle. Well, it's not next to it, so it's the opposite. So, looking at what we know, we have an angle, a hypotenuse, and an opposite. If I write out so, ka, toa, we need to find the one that uses opposite and hypotenuse. Well, looks like sine. So, I'm going to say sine of 21 equals the opposite, 1,200, over the hypotenuse, which is x. Now, I want to get x by itself, so I'm going to multiply x to both sides, so that x times sine of 21 equals 1,200. I'm going to divide 1,200 by sine of 21 to move that over. So, here I can divide 1,200 divided by sine of 21 if I'm using a calculator. If not, I may have to go to our chart. Let me get it here. Now sine of 21 looks like to be 0.3584. So I'd have to divide 1,200 by 0.3584. We're just going to use a calculator. So 1,200 divided by sine of 21 gives us that x is approximately 3,348.5 feet. Now, if we look at the problem, that's saying that we went down 3,348.5 feet down this path down the mountain. And that seems to fit. 1,200 feet elevation change, going that distance as our hypotenuse. So that's the distance we went down. Now, let's look down at this next problem. We have a skateboard ramp, and we have an angle, 26 degrees. We have 14 feet as the hypotenuse. We need to find the height, which is our x value, and the length of it, which is the base. So if I just go to set up and see how it really sets up. So first, let's try sine. If I said sine of 26 degrees, because that's the angle I have to look at, sine is opposite over hypotenuse, so that would be x over 14. Okay, I could solve that. And let's look at another one. Let's say cosine of 26 is adjacent over hypotenuse, so I can say that's y over 14. I could solve that as well, and we're going to get to both x and y. So let's do them both. Now, looking at sine first, I'm going to move this 14 over by multiplying, so 14 times sine of 26 equals x. Now I have to multiply. Sine of 26, go back to our chart here, is 0.4384, so I can multiply that by 14. I'm going to do a little bit of a shortcut and just do it on a calculator. Sine of 26. And I get that x is about 6.1. And that's 6.1 feet. Now we go to cosine, because we're going to find y, which is going to be the length of the ramp. I move the 14 over, it becomes 14 times cosine of 26 equals y. Bring over our chart again. Cosine of 26 is 0.8988. I could multiply that by 14, or we could just use our calculator and do 14 times cosine of 26, and we get that y is about 12.6 feet. So we found that the length of the ramp was 12.6 feet. The height was 6.1 feet. So these were using the sine and cosine ratios to solve problems, a little more based on an application. As we start off, though, you'll probably see more of these types of problems. It's giving you the setup and getting used to that process of solving. So it'd be a good time here to pause, or at least maybe watch a couple, then pause and try a few on your own. Because really it's getting that setup, getting that practice, and then checking back to see if you are making a mistake, where that mistake is, and how you can correct it. So let's start off with our first one. I have 44 degrees. If I look at x, you know what, let's get this written up here just to give us a reference as we go, because we're going to use sine and cosine. Tangent, not really coming up today, but maybe it does show up. Anyways, 44 degrees. If I go opposite over hypotenuse, I could say that sine of 44, which is opposite over hypotenuse, is x over 14. That becomes 14 times sine of 44 equals x. 14 times sine of 44 gives us that x is approximately 9.7. We're going to do the same thing for y, but with that 44 degrees, we're going to use cosine. So cosine of 44 equals y over 14. That becomes 14 times cosine of 44 equals y. 14 times cosine of 44 gives us that y is approximately 10.1. Okay, we'll just work our way down here. Next I have 77 degrees. I could use the radical 3, or root 3, with the y, so that looks like it would be, let's see, adjacent and hypotenuse, so cosine of 77 equals root 3 over y. If I move over the y times cosine of 77 equals root 3. Divide over cosine of 77, I get y equals root 3 over cosine of 77. We plug this in, we get square root of 3 divided by cosine of 77, and that comes out to be about 7.7. So we got about 7.7. Now I don't like to use when I have approximated to find another value. I'd like to try to stick to it, but since we want to try to stick to sine and cosine in this case, we're going to use x and 7.7 as sine of 77 equals x over 7.7. If I multiply over that 7.7, I get 7.7 times sine of 77, which gives me, we're going to keep in mind an approximation, not as accurate as I would always like, but x is about 7.5. Okay, working our way down. Next one, separate it here. 54 degrees, and I have x, and I have y. Okay, let's start with this 5.7 and the y. That's going to be cosine of 54 equals 5.7 over y. Move the y over, it's y times cosine of 54 equals 5.7. Divide by cosine 54, I get 5.7 over cosine 54. Get our value here, 5.7 divided by cosine of 54 comes out to be about 9.7. And now that we have y is 9.7, we need to go back now and find x. And let's do something different here. I'm going to use 54, but now I'm going to use opposite over adjacent to find x, just to keep with the decimal they already gave me. And that's opposite over adjacent is tangent. So I'm going to use tangent of 54 equals x over 5.7. That becomes 5.7 times tangent of 54 equals x. Which comes out to be x being about 7.8. Okay, we work our way back to the other side here. I'm going to start with, let's see, 8 and y. Well, that looks like I could do sine of 32 equals opposite over hypotenuse, 8 over y. That becomes y times sine of 32 equals 8, which then becomes y equals 8 over sine of 32. 8 divided by sine of 32 gives us approximately 15.1. Now when we find x, let's do cosine. So do cosine is adjacent over hypotenuse. Cosine of 32 equals x over 15.1, which is 15.1 times cosine of 32. And this is an approximation still because we're actually using a number we rounded already. So 15.1 times cosine of 32, and we get that it's about 12.8. Next one, we have 26. 17 and x, so that's an adjacent over hypotenuse. So let's do cosine of 26 equals 17 over x. That becomes x times cosine of 26 equals 17. Then that becomes x equals 17 over cosine of 26, which comes out to be about 18.9. And as we go, it's good to pause here and think about the other stuff we've done this chapter. If I had these two values, I don't necessarily have to use sine or cosine, or even tangent for that fact, to find y. I could use Pythagorean theorem. I mentioned tangent. We could use tangent. And there's other ways we're going to be able to get there, but again, right now, we're using sine and cosine, so we'll keep plugging in. We did throw a tangent in down here, but that's all right. So now we need to deal with y. So for y, it's going to be opposite and hypotenuse. So that's sine of 26 equals y over 18.9. That becomes 18.9 times sine of 26 equals y. So y is approximately 8.3. Okay, finishes that one off. On to our last one here. Last one, I have 14 degrees. 4 is my opposite, x is my adjacent, y is my hypotenuse. So let's start with opposite and hypotenuse. So sine of 14 equals 4 over y. That becomes y times sine of 14 equals 4, or y equals 4 over sine of 14, which comes out to be about 16.5. And I hope you can see that there. Let's move it up a little bit. 16.5. Right there. Okay, and now for x, we'll do adjacent and hypotenuse. So that'll be cosine of 14 equals x over 16.5. 16.5 times cosine of 14 equals x. So we plug that in, and we get that x is about, looks like 16.009. We're just going to call it 16.0 and round it to there. Okay, so there's our problems. We'll find sine and cosine, and maybe as we do this, you're starting to see tangent works at times. Pythagorean theorem works at times. We don't always have to be stuck with sine and cosine. We can usually work with it the better we get at it. But key thing, as you go through these, sine, cosine, tangent, that's SOHCAHTOA, get that correct setup. Any of these problems, if I used a different trig ratio, but the same fraction would not work out the same. It's very dependent on which ratio you choose. Which is why, if we look at this table, these values are not the same going across. Sine of 20, cosine of 20, and tangent of 20 are not the same values. They're not near each other. We have to be careful as we go through. So double check as you go, and good luck.